All right, hello guys. This is our last discussion on thermodynamics, looking at spontaneity and free energy. Gibbs free energy and spontaneity is what we're going to be focused on. So it can be shown that the minus T delta S of the universe equals delta H of the system minus T delta S of the system. Your book has a lovely derivation of all this stuff, so please check that out as at your leisure. The Gibbs free energy, or G, is the maximum amount of work energy that can be released to the surroundings by a system at constant temperature for a constant temperature and pressure system. So Gibbs is kind of our major player in thermodynamics. Gibbs free energy is often called the chemical potential because it's analogous to the storing of energy in a mechanical system. So looking at a reaction process and doing calculations, you can theoretically calculate how much energy could be released that could be done or used as work energy at the end of the process. Similar to a mechanical system, as a machine has the ability to do work upon something, it's stored in itself and then turn it on and use it. That's where similarity comes about. So our relationship with all our thermodynamic functions is the Gibbs free energy of the system equals the enthalpy, change in enthalpy of the system minus T delta entropy of the system. So a very important equation. It is on your equation sheet. Don't need to memorize it. Makes life easier. So we know that delta S of the universe, or the second law of thermodynamics, determines if a process is spontaneous. Delta G also determines spontaneity. And since we're not looking at the entropy of the universe, our focus here is the entropy of the system. We can also look at delta G. Since a positive delta S of the universe is spontaneous, therefore a negative delta G represents spontaneity through all the derivations of the equations that you can see in your text online. But this relationship holds true. So Gibbs free energy, or delta G, a process will be spontaneous when delta G is negative. Well, it should make sense because as energy is released, remember there's no negative energy, the algebraic sign is a direction. A loss of energy makes the system more stable. It's at a less energy state. Now, delta G will be negative when enthalpy is negative and entropy is positive, based on that equation which I showed earlier today. So basically it's saying an exothermic reaction that is making the system more random or more disordered. Delta G will be negative when H is negative and large, and S is negative but small. So an exothermic reaction that has a small change in entropy that's also negative. Delta G will be negative when enthalpy is positive but small, and the entropy change is positive and large, or at high temperatures. So there's a relationship that we're looking at here corresponding to enthalpy and entropy and how they make the numbers work out so that G is negative or spontaneous. Delta G will be positive when the enthalpy is positive and the entropy is negative. Meaning a positive number minus a negative number is always positive, no matter what the temperature is. An endothermic reaction becoming more ordered on the surface of the sun, never going to happen. Now, notice here we have delta G equals 0 when the reaction is at equilibrium. So there's no net energy change in either direction. Couple things to note here, or maybe one of them. This is delta G. Notice there is no not symbol, the little degree symbol after it. This is delta G at any condition other than standard conditions. The not symbol represents standard conditions. So delta G of a reaction is 0 at equilibrium. There is a reference sheet on my website that gives you a little bit more explanation between delta G, as you see here, and delta G naught that we're going to see shortly. Looking at a reaction regarding equilibrium with delta G, notice if I have pure nitrogen and hydrogen, it will spontaneously react to go to ammonia. If I have just ammonia, it will spontaneously decompose into hydrogen and nitrogen. Now, this is a reversible process. So at some point, it gets to an equilibrium and the delta G is 0. The delta G naught can be calculated because it's at standard conditions, or looking at the reaction at standard conditions. So all the words we kind of just said, this will kind of sum it up, if you will, based on conceptually, what does the algebraic sign of enthalpy and entropy need to be, considering temperature as well, on what Gibbs will tell us. This sheet is in the reference section of my website, so you can print it out. I'd print it out, 50%, 70% size to paste into your notes. Just so you have it, to copy this down, just have it there, make it a lot easier for you. All right, how do we calculate delta G? Couple methods. First method is we use the Gibbs-Helmholtz equation. Notice the naught symbols are here now. Delta G naught equals delta H naught minus T delta S naught. Not snot, but S naught. Using thermodynamic data from the back of your book or on the reference sheets, you can calculate H and S, plug it into the equation, and solve for G. Keep in mind, temperature must be Kelvin. Temperature is always going to be in Kelvin. Just remember that. Method 2 is looking at kind of an adaptation of Hess's law. Here we have, we will look at the reaction of diamond going to graphite. So I have the combustion of diamond and its delta G value, and I have the combustion of graphite and its delta G value. These are kind of delta G of formation values. Forgot the little F there. So I'm going to keep my number, or keep my reaction for diamond. I'm going to reverse the reaction for graphite. Notice that when I reverse the reaction, the algebraic sign of delta G changes. Oxygens cancel out, carbon dioxides cancel out, and you're left with this value. Now, this is a spontaneous process. The number is small, has no correlation to the speed of the reaction. It's just a small delta G value, but meaning that diamond eventually turns into graphite. Method number 3, looking at formation values. So you've seen this with enthalpy, you've seen this with entropy, products minus reactants. However, similarly to enthalpy, the delta G naught of formation of an element in its standard state is also 0. So enthalpy and Gibbs of formations have a value of 0. Absolute entropy of an element in its standard state has a value. Got to keep that in mind. Any questions so far? Okay. So, free energy and its dependence on pressure. So, enthalpy is not pressure dependent. You can mess with the pressure all you want. The heat transfer in the process is not going to be affected. Entropy, however, depends on volume. Well, volume also depends on pressure. If you remember Boyle's law. Hopefully you said that before I did. We know that a large volume has an entropy that's larger than an entropy of a small volume. Well, that should then go along with entropy of low pressure has a larger entropy than high pressure. Ultimately, it comes down to the arrangement of particles. Large volume, more microstates for the same macro state. Low pressure, and then so they all kind of, the volume and the pressure kind of work together. So if entropy is pressure dependent, even though enthalpy is not pressure dependent, it's going to make free energy pressure dependent. Now, here's where we get our first relationship between delta G and delta G naught. Couple things to notice about this equation. Q should stand out. What is Q? Hopefully you said Q, or capital Q, is the reaction quotient. The reaction quotient from equilibrium represents any position of a reaction process that is not at equilibrium. So if I want to know the delta G of something, of a reaction that's not at equilibrium, then the relationship of delta G equals delta G naught. Delta G naught is at standard conditions. Look it up in values. Use one of the three methods we just saw to solve delta G naught, plus RT natural log of Q. The gas constant, in this sense, is the energy constant. 8.314 joules per mole Kelvin. T is temperature in Kelvin, and that's the natural log of Q. So delta G is at some pressure P, and delta G naught is at standard atmosphere. Q is some condition, not at equilibrium. So when you're not dealing with standard conditions, there's a relationship in order to solve for what is delta G when you're not at standard conditions using the information in the equation. This equation is no longer on the equation sheet. You do not have to solve for it on the AP exam. However, understanding the relationship of variables is what's going to help you, because you should be able to figure out, if you know what's happening with Q and you know the log of x, the natural log of x graph, you can figure out if RT natural log of Q is a positive or negative number, and is that going to be added to or subtracted from delta G naught, and therefore you know what delta G, how delta D is changing. Delta G, sorry. Any questions? So now we get free energy and equilibrium. So now we're dealing with an equilibrium process. So we know equilibrium is the lowest point, or the lowest value for free energy available to the system, because it's going to be zero. Energy is no longer released or absorbed. So the equation we just saw, delta G has to be zero. And therefore Q has to equal K. My equation will come up here shortly. But if you take the previous equation that we just saw, if delta G is 0 and Q is now K, you can rearrange the equation. Well, if delta G naught is 0, according to the equation, what does K have to be? Hopefully you came up with 1, because the natural log of 1 is 0, and anything times 0 is 0. This condition is theoretical. Any equilibrium reaction isn't going to get to a perfect equilibrium of 1, where the delta G naught equals 0. So delta G naught basically never reaches 0, because K will never equal 1. If delta G is negative, is that reaction spontaneous or non-spontaneous? Spontaneous is the answer. If it's spontaneous, what direction is the reaction going in? Forward direction. If it's a forward direction reaction, am I product favored or am I reactant favored? Product favored. If I'm product favored, what's my value of K, or the equilibrium constant? Greater than 1. Yay. All right, delta G is positive. Does that mean it is spontaneous or non-spontaneous? Non-spontaneous. If I'm non-spontaneous, is there reaction really occurring? Or what direction is it going in? Going to the left, not really occurring. If I'm a reactant favored equilibrium, what's my value of K, or the equilibrium constant? Less than 1. So this relationship you see on the screen in the blue teal box thing, very important, because you're not doing any calculations. You solve for one or the other one. If you solve for delta G, you automatically know what the equilibrium constant is going to be. Maybe not the answer specifically, but you can tell where the equilibrium lies. So again, the relationship of variables is very important to understand. Which brings us to our not equation. I thought I had the equation written down, but we'll get there. So moving on, sorry. So we have this equation, which we already saw, which then rearranges itself to delta G naught equals a negative RT natural log of K when you are dealing with an equilibrium condition. Remember, the top equation, not on the equation sheet, and deals with delta G at some other pressure. And the second equation is delta G naught, standard conditions, dealing with an equilibrium condition, where our gas constant now becomes our energy constant, 8.314 joules per mole Kelvin. Got to keep that one in mind. It is on your equation sheet, so don't worry. There's a link here to delta G versus delta G naught explanation, so please check that out. It is in the reference section, which I think you probably already have maybe printed out possibly, so make sure you check that out. All right, temperature dependence of the equilibrium constant. You learned in equilibrium that equilibrium reactions depend on temperature. The numerical value of equilibrium never changes as long as temperature is held constant. So we know delta G naught equals these two equations. Well, if delta G naught equals these two equations, then I can set them equal to each other. Notice that the equilibrium constant is there, right here, and temperature is also there. Do some rearranging. I get this lovely mathematical thing, where if we get rid of the middle part, we can see that the natural log of K is directly proportional to 1 over T. And our equation of our line of y equals mx plus b, where the slope is negative change in enthalpy over r, and our b constant, positive change in entropy over r. So again, this is not on your equation sheet, but it is proving that the equilibrium constant is dependent on temperature. As temperature changes, depending on if the process is exo or endothermic, the numerical value of the equilibrium constant will also change. So very important relationship of variables. Questions? All right, we have some practice problems here. I'm going to pause each one for a little bit and let you do it. So please do this one. And now moving on. Any questions? Next problem. Pause. And now moving on. Any questions? Next one. Pause. Moving on. Questions? Moving on. Pause. And moving on. Questions? Next problem. Pause. And moving on. Next question. Pause. And moving on. Questions? Next question. No more questions. Yay. All right, thank you very much.